Hi everyone, today we're going to talk about entropy. Title: Learning Objective from College for students able to use representation and models to predict the sign and relative magnitude of the entropy change associated with chemical or physical processes. What is a spontaneous process? It is an irreversible, thermodynamically favorable process that goes on its own without any outside intervention. Now, historically, this has been referred as spontaneous process, but nowadays we tend to call it thermodynamically favorable because we cannot make a spontaneous process more spontaneous. So the thermodynamically favorable makes a lot more sense. So what are the driving forces? For example, how come waterfall would go downhill? That if you dissolve sugar in coffee, it will dissolve by itself. That the gas will expand to fill the vacuum. That heat will flow from hot to cold objects. That iron will form rust when exposed to water, humidity, and oxygen. And sodium metal reacts violently with water, and wood burning goes on spontaneously and exothermically to form CO2 and water. The question is enthalpy the driving force, delta H? Enthalpy means that a system has a tendency to reach minimum potential energy. Now let's look at the combustion of methane. This is highly exothermic, delta H is negative. Now let's look at the solution of ammonium nitrate, and this is endothermic. The solution actually becomes cold. So how do we account for enthalpy being the driving force when we have it happening both for endo and exothermic reactions? Let's go to the law of thermodynamics. The first law says, energy can neither be created nor destroyed. Energy of the universe is constant and can be converted from one form to another. The second law says that in any spontaneous process, there's always an increase in the entropy of the universe. Now, what do you mean by entropy, delta S? It means the tendency toward randomness. It is the driving force of a spontaneous process according to the second law of thermodynamics. Entropy increases when, 1, when matter is dispersed by phase change from solid to liquid or liquid to gas, because now particles will occupy greater volume and have more freedom to move. So you can see that the entropy change of gas is greater than that of the liquid, which in turn is greater than that of the solid. Another factor affecting entropy change is the stoichiometry of a chemical reaction. When there are more moles of product formed than the moles of reactant, the entropy change increases. Or if the volume is increased to allow the gas molecules to move within a larger space, that means the entropy increases. Or if there's a change in temperature, when temperature is elevated, that will spread the distribution of the kinetic energy of gas molecules more broadly. If you remember the Maxwell-Boltzmann distribution curve, and that will increase the randomness or the entropy change. Now, entropy is a state function independent of the pathway. So entropy change is entropy final minus entropy initial. When final state becomes more random, meaning entropy increases, and we designate it as positive. When final state becomes more orderly, meaning entropy decreases, we designate it as negative. In practice, problem number 1. Predict the sign of entropy change of the system for the following. Let's look at the first one. 1 mole of nitrogen and 2 moles of hydrogen to form N2H4. As you can see, we're going from 3 moles of reactant to 1 mole of product. Entropy decreases, it's negative. The next one, we have equal moles of reactant and product. There's no change in entropy, which is equal to 0. This one here is showing solid iodine and bromine liquid to form iodine bromide, the gaseous molecule. A gas is more random than liquid, than solid, therefore entropy increases positive. When lead ion and iodine ion collide to make the precipitate yellow lead iodide, entropy decreases negative. When gases chlorine molecule dissociate to form 2 moles of chlorine atom, there's a greater number of atom than molecule, entropy increases positive. And finally, looking at this diagram, we have 4 moles of gases molecule on both sides of the container. Now they all go to one side. That means it's becoming more orderly. So entropy decreases. So which has greater entropy? 1 mole of neon in 15 liter or 1 mole of neon in 1.5 liter? Clearly, it's the one that has larger volume, more room for the neon to move. 15 liter has greater entropy. Is it half a mole of nitrogen or methane at the same pressure, volume, and temperature? Well, methane weighs less than nitrogen, so it would be able to move faster and probably creating greater entropy. Is it 1 mole of water ice or 1 mole of water liquid? Has to be the liquid because liquid is not touching one another, not locked in place. It slides past each other, greater entropy. Entropy of the universe. According to the second law, that the reaction, if they increase in the entropy of the universe, will be spontaneous. Now, reaction that means it decreases the entropy of the universe, then it's non-spontaneous. The entropy of the universe is made up of the entropy change of the system and the entropy change of the surrounding. For the universe change to be greater than 0, the absolute value of the entropy change of the surrounding must be greater than the entropy change of the system. Now remember, the surrounding and system, they usually are opposite in sign. When the surrounding becomes greater in entropy, that means the system could be more orderly. In exothermic reactions, such as freezing and condensation, heat is released into the surrounding. That means energy is dispersed, increasing the entropy of the surrounding, which is positive. In endothermic reactions, such as melting and evaporation, heat is absorbed from the surrounding. That means the entropy change of the surrounding decreases, which then is negative. Although enthalpy change by itself cannot determine the spontaneity of a process, an increase in the entropy of the surrounding caused by heat released explains why exothermic processes are often spontaneous. Why does water freeze spontaneously at low temperature 0 degrees C, but not at high temperature like room temperature? Well, remembering delta S of the universe is made of 2 components, that of the system and the surrounding. When ice is formed, heat is released to the surrounding. That means the randomness of the system now decreases. At low temperature, the heat released by the system into the surrounding has a greater impact on the entropy of the surrounding. So this delta S of surrounding is large positive, whereas the delta S of the system is more negative. And overall, the net effect on the entropy of the universe will be positive, spontaneous reaction. At high temperature, the heat released by the system has a smaller impact on the entropy of the surroundings. Now, when I say high temperature, I mean temperature of the surrounding. So this entropy change of the surrounding will be small positive, while the entropy change of the system will be a large negative, resulting in overall the entropy change of the universe being negative, meaning the reaction is non-spontaneous. So what I just said is referring to these 2 diagrams. On the left-hand side, we have a positive delta S surrounding and negative delta S system. So your overall delta S of the universe is small positive, spontaneous. On the right side diagram, you have a small positive delta S for surrounding and a large negative for delta S for system. So the overall delta S of the universe is a small negative. Reaction is non-spontaneous. Delta S of the surrounding depends on temperature. When heat is released to the surrounding, meaning negative Q of the system. Remember, system and surrounding are opposite in sign. So the entropy of the surrounding will increase, which is positive. That means the temperature of the system decreases. When heat is absorbed, that means the system has a positive sign for the Q. The entropy of the surrounding decreases, negative, and the temperature of the system increases. So we can conclude that the entropy of the surrounding is directly proportional to negative Q of the system, Q referring to heat energy, but inversely proportional to the temperature. So the delta S of the surrounding is negative Q system over T, T referring to that of the surroundings. And at constant pressure, the Q of the system is equal to delta H of the system enthalpy change. So we now derive a new equation that the entropy change of the surrounding is negative enthalpy change of the system over temperature in Kelvin. Let's try practice problem number 2. Combustion of ethanol giving heat negative 1235 kJ per mole released. Calculate the entropy change of the surrounding at room temperature. Now we can apply the earlier formula and put in negative of a negative 1235 kJ over 298 Kelvin, resulting in the entropy change of the surrounding being 4.14 kJ per Kelvin. Let's decide on the sign of the entropy change of the system. Remembering that we are going from 3 moles of gas into actually 5 moles of gas product, not 4, 5 moles of gas product. So the entropy change of the system is increasing, which is positive. Therefore, the entropy change of the universe based on 2 positive signs will be positive. That means the reaction will be spontaneous. To sum up what we have learned today, we learned that entropy is the driving force of any spontaneous processes according to second law of thermodynamics. That we also learned the conditions under which entropy will increase in a process. We learned to predict signs of entropy and thermodynamically favorable processes. The entropy of the universe is made up of that from the system and the surrounding. And the entropy is dependent on temperature. I hope that you have found this video helpful to you. If you like it, please give us a like. And I hope to see you in the following part of this entropy video.